Okay, we'll go ahead and get started. Can the people on Zoom hear me okay and see the slides?
Yeah, we can.
Thank you. All right, so a couple things I want to mention before we get started on the rest of the thermochemistry. So just a reminder that next week, next Wednesday, we'll have an exam. That'll cover chapters 3 and 4, so it won't cover the thermochemistry, but it'll cover chapters 3 and 4. So Monday, we should get finished with thermochemistry today. So Monday, we'll just spend some time reviewing chapters 3 and 4 to get ready for the exam on Wednesday. I also wanted to mention that I did go ahead and post my answers to the homework for chapters 3 and 4. So when you start studying for that stuff, if you want to go back and rework some problems and do some things like that, if you have questions, I have posted my working out of the homework. So you can look at that. You can certainly always send me a message or come by my office or something if you have a question also. So, okay. So today we're picking up again with the second half of the thermochemistry lecture. And we touched on this a little bit on Monday, the idea of calorimetry and a calorimeter. So the calorimeter is used in order to determine some of these delta H values, some of these enthalpy values. And this is a pretty simple calorimeter. This is the type of one you'll use next semester in a lab. It's pretty common in Gen Chem classes where you have kind of the styrofoam cup within a styrofoam cup. All you're trying to do is insulate the system real well so that then you can measure the heat flow without a lot of the heat escaping from the system. So they work pretty well for demonstration purposes. We'll talk about some other types of calorimeters in a few minutes, but this is kind of a basic model which allows you to kind of get the idea of how these measurements are done. What I'd like to do now is talk about heat capacity. And there's three ways that we define heat capacity. And basically, thinking about heat capacity, it's everything has the ability to take heat on. And some things can take more heat than others. That's the simple definition of heat capacity. The technical definition is it's the amount of energy required to raise the temperature by one Kelvin or 1 degree Celsius, either one. That's the definition of heat capacity. Now, if you're talking about the heat capacity of a desk or something, an object like that, it tends to be just heat capacity. When you talk about substances, so compounds and things like that, then it's common to express it in one of two ways. One is specific heat, and that's the amount of, it's the amount if the substance is 1 gram. And so if you have, it's a per gram value, and that's a capital C with a small s subscript. There's also molar heat capacity, which is designated as a capital C with a small m subscript. So if it's capital C S, that's on a per gram basis. If it's capital C with a small m, that's on a per mole basis. So one of the things is when people give you a specific heat value, you want to just check and see which it is. So this table here, you see some specific heat values. In that case, it's on a per gram basis, so it would be the C sub S if you were to see the symbol for that. But what they all have in common is whatever the units are, it's how much heat do you have to put in to get a 1 degree change in that material. So let's take a look at the specific heat equation. Specific heat is equal to the quantity of heat transferred divided by, in this case, grams of substance times the temperature change. And so if we put that into with mathematical symbols, it's CS equals Q over M times delta T. We can rearrange that equation if we want to find that quantity of heat, because oftentimes we know the specific heat. There's tables of specific heat out there. So a lot of materials have had their specific heat already determined experimentally, and people put these in tables and they're available. So sometimes you know the specific heat, but you're trying to figure out what it would be, what the heat energy transfer, what the heat flow would be for a particular amount of material. So in that case, you would know M, the mass, you'd know how much material you're dealing with, and then you could experimentally measure a change in temperature. That's where using that calorimeter would come into play, where you do the reaction or do whatever it is process you're doing, and you have the initial temperature and you have the final temperature. So you have your delta T value there, you have the mass of how much material you're dealing with, you would have the specific heat from a table somewhere, and then you could calculate how much heat was transferred, how much energy was transferred. Another type of calorimetry is called constant pressure calorimetry. And these kind of simple calorimeters like this is going to be constant pressure, because you think they're done at atmospheric pressure in this type system. And so atmospheric pressure is essentially a constant pressure, 1 atmosphere. So in this case, you have an aqueous solution. You're going to do some type of reaction in there. It's usually a dilute solution. Because it's a dilute solution, we can just use the specific heat for water, which is known to be 4.184 joules per gram Kelvin. Because it's a real dilute solution, we can use that value for it in our equation as the CS term, and then have mass and then temperature change. And from that, we can calculate that heat flow for that reaction. So that styrofoam cup kind of calorimetry experiment is a nice experiment to do for demonstrating some of these principles and things like that. But the way it's done when people are trying to get data to calculate some of these constants, to actually get delta H values, it's usually some type of bomb calorimetry. And so I want to talk about that for just a few moments. So there's a bunch of different types of bomb calorimeters, but here's what they kind of have in common, is that it's sealed up, and that's why it's called a bomb. And usually it's pressurized, so you can put some amount of pressure in there that's known, kind of in contrast to the constant pressure, just atmospheric pressure type situation. Often it's oxygen that's put in there, and so you're doing combustion reactions. You can do other kinds, but this is a pretty common thing. And so what you see here is you see a little reaction chamber. It has ignition wires to it. You put your sample in. There's oxygen in that chamber so that it will combust, and you basically blow the sample up. You're measuring the temperature of the water that's surrounding that, and you get a before and after, and that's your delta T value. The one thing about these types of setups is that you have something called a calorimeter constant, and that needs to be taken into account for this. And what the calorimeter constant is, it gives you a feel for the heat interaction for the whole system. And the way you calculate what that is you'll take a material, often it's benzoic acid, and you'll take a material which is really well characterized, and you kind of know what the answer should be, and you do the experiment and you see what kind of adjustments you make. So basically what you're doing is you're kind of calibrating the bomb so that then when you do your actual sample, you know what adjustments to make to get the right answer. So this bomb calorimeter, this is actually one way in which they'll figure out like how many calories are in food and things like that. Because the volume in the bomb calorimeter is constant, technically you're measuring a change in internal energy, delta E, and not delta H. The reality is that those numbers are usually pretty much the same. So people usually kind of just say delta H. Let's talk about Hess's law. So for a lot of reactions, delta H is known. So people have done the bomb calorimetry experiment or something similar and determine what delta H is. And so you don't want to have to go and repeat that work all the time. So there's literally tables of delta H values for reactions that are out there that are published. And so, excuse me, you can use those values to calculate out what the predicted delta H value would be for a reaction that you're studying. And the key to this is that Hess's law, the delta H is a state function. And so Hess's law allows us to go ahead. Remember, a state function is one that it doesn't matter the path you took to get there. It's that beginning to end difference that's important. And so we can piece together intermediate reactions to get to that final reaction. And by knowing those delta H's, we can do some math and calculate what it is for the final reaction. Okay, so as I said, if the reaction can be carried out in a series of steps, the overall reaction equals the sum of those enthalpy changes for the individual steps. And so here's an example of where two different ways you got from the starting reaction to the products. One was direct, one had an intermediate step, but the enthalpies add up, so you get to the same spot. That's the idea behind the state function, is you can piece it together different ways, but the energies are the same. And that's very useful when we go and try and do some calculations to see what the delta H for a reaction should be. Okay, so what I'd like to do now is, here's some homework problems that you can take a look at. What I'd like to do is I'd like to go over a few of these just so everyone's kind of clear on how to do some of these homework problems. So let me get my book out here. So the first one we'll take a look at is 5.43. So in this reaction, it tells us that we have this reaction, magnesium plus oxide, plus oxygen rather, giving us magnesium oxide, and it gives us a delta H value. And then it asks us, the first question it asks, is it exothermic or endothermic? So the delta H value for this reaction is minus 1204 kilojoules. Is that exo or endo?
So
Why is it exo?
because it's releasing it to the environment, so it's negative from the system.
Right, it's a negative delta H. So if by definition, if it's negative, it's exothermic. It's giving off the energy, giving off the heat. Okay, so then in part B, it says calculate the amount of heat transferred when 3.55 grams of magnesium reacts at constant pressure. So a couple things that should come to mind when we see that. We see that we're given a gram value, and we want to get that over to a kilojoule answer, kilojoule units in our answer. Whenever we have grams and we want to change into some of these other units, one of the first things that could kind of go through our mind is, I'm probably going to have to get things in moles, because moles is really the nice unit that allows us to kind of move amongst the different grams, moles, kilojoule, things like that. Hold on a second. So we start with 3.55 milligrams of magnesium, and then we change that into moles. So we need the atomic weight of magnesium. That's the 24.3. So now we've converted into moles. We know from our reaction up front that delta H for this reaction is minus 1204 kilojoules. But what we also see is we're interested in the coefficients for each of the molecules that we're dealing with. In this case, we see that for this reaction, you're using 2 moles of magnesium to make this reaction go. So I have to have the association of 2 moles of magnesium with that amount of energy, with that minus 1204 kilojoules. So changing moles of magnesium to kilojoules, I need to have the kilojoules over 2 moles of magnesium, so the moles of magnesium cancel out, and then my final units are kilojoules. And if I go ahead and do that math, then I get minus 87.9 kilojoules. So the important things to remember on this problem, one was I was given grams, so I wanted to get that into moles, so I needed to know atomic weights, molecular weights, things like that. And then I wanted to check the coefficients on my balanced equation. Once again, this is why balancing equations is important, because it tells us when we do reactions, how many moles of the different components are going to be involved in that. And in this case, it's 2 for the magnesium. So I had to put 2 in the denominator for that last conversion. Okay. Then in C, it wants to know how many grams of magnesium oxide are produced during an enthalpy change of minus 234 kilojoules. So there, this is kind of like going the other way from the part B question. Instead of being given a mass, we're given an energy, in this case, minus 234 kilojoules. And then we know that we can have this relationship by looking at the stoichiometry on the reaction to know how many moles of, in this case, magnesium oxide are associated with that delta H value. We look up at our equation and we see there's 2 moles of magnesium oxide formed. And so we have the minus 1204, our delta H in kilojoules in the denominator. So that'll cancel out those units on the kilojoules. And then we have 2 moles of magnesium oxide in the numerator. We've now switched over to moles of magnesium oxide. We said that we wanted our answer in grams. So then we calculate the molecular weight of magnesium oxide, and that turns out to be 40.3. So that's in the gram values in the numerator, 1 mole of magnesium oxide in the denominator. You go ahead and complete that calculation, and it's 15.7. So needed to calculate a molecular weight here, need to use the coefficients on our balanced chemical equation. And by using those things, we were able to come up with our answer. So a couple things should be coming in mind for you. One is, we've talked about dimensional analysis quite a bit this semester. Here's another example of using dimensional analysis to convert, in this case, from kilojoules to grams, previously from grams to kilojoules. And also it shows the importance of moles, and so need to be comfortable calculating atomic weights, molecular weights, things like that. Let's look at the last question on this, D. In D, it says how many kilojoules of heat are absorbed when 40.3 grams of magnesium oxide is decomposed into magnesium and oxygen at constant pressure. So I look at that and I see the key thing is 40.3 grams of magnesium oxide. I'm trying to get to an energy value. So I know that I'm going to have to get into moles and then use the stoichiometry on my equation to get it into my final energy value. So if I start with 40.3 grams of magnesium oxide, once again, there's my molecular weight of 40.3 in the denominator. You cancel those grams units out. Now I'm in moles of magnesium oxide. I go back to my equation and see there's 2 moles of magnesium oxide. So 2 moles, except now I have plus 1204 kilojoules. I thought my delta H was minus 1204 kilojoules. Why did I write plus 1204 kilojoules? Well, what did we say? We were looking.
It says absorbed instead of dissipate out.
It says absorbed, but the other thing is, which direction is our reaction going? It's going to the left. And remember, one of the things we said about delta H, I think we said this on Monday, is that if you write the reaction this way and you say delta H is minus 1204 kilojoules, that's for the reaction going from left to right. If you take the reaction the other way, delta H is the same magnitude, so it's the same number, but it's the opposite sign, okay? So what you said is right about the absorbing, that's correct. But in my mind, I just look at it simply as, okay, delta H going, the formation reaction is minus 1204. So if I'm going the other way on the reaction, it's the same number, but I got to change the sign. So a few things that we learned here on this problem. One is, in A, if it's a negative number for delta H, it's exothermic. If it's positive, it's endothermic. In B and C, we had examples of where if you start with a mass and are given some delta H value, you can convert that to an energy value. Key being that we have that balanced chemical equation and we look at the coefficients and factor those into our calculation. We also saw we could go the other way. If we have the energy number, we can calculate back and get a mass. And then finally, another one where we had a mass and wanted an energy, but we looked at the reaction going the other way. Because the reaction was going the other way, we knew that the number's the same, but the sign had to be changed. Because we know, by definition, the magnitude of the delta H doesn't change, but the sign changes depending upon which direction the reaction is going. Okay, let's do another homework problem. Okay, 551. So in 551, it's another specific heat type problem. So what is the specific heat of liquid water? So that's one of those things that you just look up. So the specific heat of water is known. It's 4.18 joules per gram Kelvin. Then in B, what is the molar heat capacity of the water? So if it's the molar heat capacity, we said by definition, instead of being joules per gram per Kelvin, it would be joules per mole Kelvin. So what we simply need to do is we need to replace the grams unit in the denominator with moles. If we write it out and look at our units, we see we have joules in the numerator, grams and Kelvin in the denominator. So to cancel that grams out, we need to have grams in the numerator and moles in the denominator when we do our dimensional analysis. 18 is the molecular weight of water. So 16 plus 2 is 18. So then it's just a simple math problem from there. And we get 75.4 joules per mole Kelvin. In C, they're asking what is the heat capacity of 185 grams of liquid water? So We have 185 grams. We knew from part A that the specific heat for water was 4.18 joules gram Kelvin. So if we simply do that multiplication, our gram units cancel out, and we get 774 joules per Kelvin. Then in D, move this to the top. In D, the question is, how many kilojoules of heat are needed to raise the temperature of 10 kilograms of water from 24.6 to 46.2? So we think back to our equation. Heat capacity is energy divided by mass divided by delta T. So we're given that CS value, that specific heat value, and so it's 4.18. We need to enter the mass in. So let me ask you this question. I have 10 times 10 to the third. Why do I have that? It said it was 10 kilograms. Why did I put the 10 to the third in? Yeah.
How to change it to grams.
Had to change it to grams. And so 1 kilogram equals 1,000 grams. So that's a case of where you needed to remember that conversion factor, because if you left it in kilograms, you'd get an incorrect answer. Because our units on the CS for water are joules per gram per Kelvin. So we need to get those units in there. Okay, so I just preached about units, but yet I have 46.2 minus 24.6 there. That's Celsius. My units aren't going to cancel. In this case, it doesn't matter if it's Kelvin or Celsius because it's a difference. Okay, and a difference of 1 Kelvin or a difference of 1 Celsius is the same thing. And so if I was good, I would add 273 to each of those, but I would still get the same difference. So I was being a little bit lazy there. Then you solve for Q, and you would get 903 kilojoules. Once again, I was a little lazy there. My units are joules, so if it's kilojoules, what does that mean? Yeah, is that it was really 903 times 10 to the third joules. And so, because once again, kil is 1,000. And so I just shortened it. So I should have wrote it out better, but I did not. Okay. Any questions so far on any of the problems we've looked at? Okay, let's do another one then. 553. Okay, in this they're telling us the specific heat of octane is 2.22 joules per gram Kelvin. And they want to know how many joules of heat are needed to raise the temperature of 80 grams from 10 to 25 degrees. So we use our formula, the same one that we used here, Q over mass times delta T. So we're going to use that formula again. We have 80 grams. We have 25 degrees minus 10 degrees. So we have our difference there. And we solve, and we get 2.66 times 10 to the third joules, or 2.66 kilojoules. Then in B, they're asking us, which will require more heat? Increasing the temperature of 1 mole of octane, or increasing the temperature of 1 mole of water. So we want to go ahead and do the calculation for each of those. So first, let's do the octane. So we have moles, we'll need to get that into grams because our constant was joules per grams Kelvin. So the molecular weight of octane would be 8 times 12 plus 18 times 1. So that comes out to 114. And then we multiply that by the CS value of 2.22 to get 254 joules per Kelvin. For water, that molecular weight is 18. So 16 for the oxygen and 2 times 1 for the hydrogen. So we convert the 1 mole of water into grams of water, and then use that 4.18 value that we had gotten earlier, we had looked up earlier, and we see 75.4 joules. So what that tells us is the octane requires quite a bit more heat than the water does. So because it's 254 versus 75.4. Let's look at 557. So in 557, we're told we have 2.2 grams of quinone, and it's burned in a bomb calorimeter. And the calorimeter's heat capacity is 7.854 kilojoules per degree C. The temperature change within the calorimeter is it went from 23.44 degrees C to 30.57 degrees C. And it wants to know the heat of combustion per gram of quinone and also per mole of quinone. So we take a look at this problem, we see we have a weight of quinone, we have a heat capacity for our calorimeter. And so we think back to the formula we talked about a few minutes ago when we were talking about calorimeters. And so the Q reaction is equal to minus the calorimeter constant times delta T. We were told the calorimeter constant was 7.854, and our delta T, if we subtract those numbers, is 7.13. We do that math, and we get a value of minus 56 kilojoules. If we want that on a per gram basis, then we simply divide that by the number of grams. It was 2.2, and then we get minus 25.5 kilojoules per gram. If we want it on a per mole basis, then we need to convert that 2.2 grams into moles by using the molecular weight. In this case, the molecular weight is 108.1. And then we get a value of minus 2.75 times 10 to the third kilojoules per mole. So here we use that formula that we had earlier when we talked about the bomb calorimeter. Use that calorimeter constant that we were given, and then did some conversions to get it into grams or moles or whatever units we wanted. Okay, now 5.65. Let's take a look at this one. So this is kind of an example of the Hess's rule. Is we have a reaction, C2H4 plus 6F2 going to 2CF4 plus 4HF. And then it gives us some information on individual reactions that could be part of the steps that you go through to get to the final product. So we see information on H2 plus F2 to give us 2HF, and we see a delta H value associated with that. We have C plus 2F2 going to CF4, and we have a delta H value for that reaction. And then finally 2C plus 2H2 going to C2H4, and we have a delta H value for that as well. So what we want to do is, we know what the overall reaction is. We're told that in the beginning. So what we need to do is we need to arrange these intermediate reactions in a way that it will give us that reaction at the top of the page. So the first thing I see is when I look at the things that are on the left of the arrow, so the reactant side, and the things on the right of the arrow, the product side, in the intermediate reactions, and compare it to what's in the final reaction, I don't see any C2H4. I don't see any of that on the left-hand side. So the first thing I'm going to do is I'm going to flip that reaction around and rewrite it. And that's what you see down here in this next set of reactions. You see C2H4 going to 2C plus 2H2. Because I flipped that around, you notice that the delta H value is now minus 52.3. That's similar to what we said on that earlier problem, is the reactions delta H value, the number doesn't change, but the sign changes if we flip it around and have the reaction going the other way. We had to do that because the way the first three were written, we had no C2H4 on the reactant side. And we know we want that. And that's the only one of these intermediate equations that has C2H4 in it. So we had to flip that one around. Then we get to the H2, F2 going to HF. That's okay written as is because we have HF on the right-hand side, and that's where we want it. The other equation, C plus 2F2 going to CF4, we don't need to flip that because we've got CF4 on the right-hand side, and that's where we want it. So if we look at all those, then the next thing is, our favorite thing to do is we have to balance things out, okay? We want a balanced equation at the end. And what we start to see is, the way it's written now, we're not balanced. For instance, if you look at the C plus 2F2, there's only one CF4 there. We know in our final equation we need 2. So we can simply multiply all that by 2. Then we have 2C plus 4F2 plus 2CF4. So then that would balance. The same thing with that HF. We want 4 in our final reaction, right? In our intermediate reaction, we only have 2. So we need to multiply all of that by 2. So that gives us 2H2, 2F2 going to 4HF. Remember we talked about on some things there was something called spectator ions and we would cancel those out? This isn't exactly the same, but it's kind of a similar idea. When we look at this, because these aren't ions, they're molecules, but they're compounds rather. And so when we look at this, we go and we say, okay, we've got the same thing on each side of the equation. We can cancel those out. And that's what we go back and do. The 2C on each side, we cancel that. 2H2 on each side, cancel that. Then if we add up all the things on the left and all the things on the right, we see on the left we have C2H4, we have 2F2 plus 4F2, so that's 6 F2s. And then on the right-hand side, we have 4HF, and we have 2CF4. And lo and behold, that reaction at the bottom matches the one at the top. So we've got things set up the way we want it now. So then what we can do is go over here to the right and use our delta H values to calculate an overall delta H for this reaction. The first one, the C2H4 going to 2C plus 2H2, we talked about that. Because we flipped that around how it was written when we got our delta H value, we keep that number at 52.3, but we change it from a positive 52.3 to a negative because we're going the other way on that reaction. The other two, the 537 and the 680 for the H2 plus F2 going to HF and the C plus F2 going to CF4, those, you see, we have 2's in front of that. Why do we have 2's in front of that? Yep, because we had to multiply them by 2 when we were getting our intermediate equation straightened out. So because of that, that tells us we have to multiply the delta H for each of those by 2 because it's double that's in there. Okay? So then you go ahead and do the math and you get the value. But the thing I want to stress is, what did we do? We looked at that equation that we're trying to work with, we're trying to get to. We looked at some of these intermediate reactions that can help explain that equation. And we had delta H values on those. Then we had to arrange those equations in a way that they add up to be the reaction that we want. Okay? And because of Hess's law, because of the state function, because of all that, we can use the delta H's for these intermediate reactions, and we can add those up to get what it is for this reaction. So in other words, instead of us trying to figure that out, we could use some information that was out there already to figure out the delta H for this overall reaction. So that doesn't necessarily mean those steps are actually happening in the reaction itself, but it's just saying you can piece it together through this. Yeah.
On a previous question, you calculated the kilojoules and it was positive. Do we have to put the positive sign or should we not?
You do not have to put the positive sign. The only thing I'll say though is for these types of problems, these thermal problems, if it's negative and you don't get it, you don't put negative, then that's real important. And so you don't have to put the positive, but for me, I put the positive. Delta H values tend to have the positive on them, just so people know that it wasn't, I didn't forget it or something. And so, but technically you don't have to put it on there. But like I said, when we started this chapter, we said there were 3 things that were important. One's the number, one's the units, and the other is the sign. Because in thermochemistry, the sign is more important. Not that it's not important other times, but in this, it's really important. So, okay. Any questions about this problem? Okay. So we'll go back to some more of the lecture then. So the fun thing about enthalpy is there's a lot of different types of enthalpy. So there's delta H and there's a lot of subscripts with it. Another one that we'll talk about is enthalpy of formation. So that's delta H, so the triangle, capital H, and then a small subscript F. And this is defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental forms. It's more commonly known as a heat of formation. So usually people say heat of formation rather than enthalpy of formation, but they're the same thing. And so this is just telling you what that enthalpy change is for like the reaction in its most basic form to form certain compounds. These are almost always measured under standard conditions, which is 25 C and 1 atmosphere of pressure. So typically the numbers that you get in tables, and you know it's standard by, do you see the little 0 superscript over the F? So if we go back here, we had delta HF, there wasn't that little 0, but standard enthalpies of formation have that little, I can point to you guys, but that has that little 0 there, and that's how you know it's a standard enthalpy of formation. And because of that symbol, you know when they did it, it was done at 25 C and 1 atmosphere. So here's just some standard enthalpies of formation for some different compounds. You don't need to know this, you don't need to memorize it. It's just to kind of show you the range of enthalpies that are out there for this formation. They tend to be exothermic, as you could see. There's a couple in here that are endothermic, but they tend to be exothermic, but range of values. Okay, let's talk about calculating delta H some more. So here we have a reaction of propane plus oxygen going to CO2 and water. What kind of reaction is this?
Combustion.
Combustion. And you know that because there's oxygen, O2 involved. Have any of you ever done this reaction?
The propane.
Yeah, it's the Bunsen burner. This is what happened. This is your Bunsen burner. So your Bunsen burner has propane in it. There's oxygen from the air. That's why you're regulating that little upper band. You get oxygen in, and it's forming CO2 and water. So imagine this as if it occurred in 3 steps. The first is the decomposition of the propane to elements. So propane degrades to carbon and hydrogen. And so there's a enthalpy associated with that, a delta H associated with that. Then you form CO2. So carbon plus oxygen gives you CO2. There's a delta H associated with that. That's number 2 on the chart. So we've got a decomposition. And so if we look at that for a second, that's the number 1 on the graph. That's endothermic. So it's going up. Then the second one is exothermic. So it's going down. And we know that because the signs are positive and negative. The third step is formation of water. And we see on 3, they're telling us that one is exothermic as well. And so we're getting how you could get to that point from a 3-step reaction. We also can see that there's another path where it's basically a different route. It's more, and so, but you get to the same point at the end. This goes back to that state function stuff, is that you can piece together different paths, but the key is if the equation balances, you should get to the same delta H value. So if we looked at all the steps, we wrote those 3 steps down, they'd look like this. And sure enough, if we went back and did that balancing, like we did on one of the homework problems a little while ago, we would come up with that same reaction. Now, if we were going to calculate delta H, we'd use Hess's law. We'd sum the products minus the sum of the reactants. So those formation constants for the products minus the formation constants for the reactants, and taking into account for each of the products and each of the reactants, what's the stoichiometry coefficient for each of those molecules. So we're going to take a look at an example of this in a moment. There's our reaction, okay? And we said it's the sum of the products minus sum of reactants, right? Go back here to this. Sum of products minus sum of reactants. So we're going to sum the delta H's of the products and then subtract the sum of the delta H's of the reactants. So the products would be CO2 and water. So we see that we have 3 moles of CO2. So we have 3 times the delta H of CO2. We then have 4 times the delta H of the water. That's the minus 285 number. So we have those 2 values. We're going to sum those up together. Then we have 1 of the propane, so that's the C3H8, and that molecular weight is 103.85. Then plus 5 times the oxygen value. For oxygen, it's 0. So now we have our products minus our reactants. We sum up those two things. You can see the math there, and we get our final value of minus 2219.9 kilojoules. Let's talk about another kind of enthalpy, bond enthalpy. So the enthalpy associated with breaking 1 mole of a particular bond in a gaseous substance is called bond enthalpy. And once again, just like with some of these other enthalpies, there's tables out there that give you this kind of information. And you can use that information to do some estimates of delta H values. So we're going to look at that for a bit. Bond enthalpy is always positive because you got to put energy into bonds to break them. Okay, so breaking the bonds is always endothermic because you got to put energy into it. Energy is always released when a bond forms between gaseous fragments. And the greater the bond enthalpy, the stronger the bond. And so let's take a look at a table of some bond energies here. So what you notice is that, as we said, they're all positive because you got to put energy into it to break it. And the higher the number, the stronger the bonds. So the other thing I would point out here is, if you're not familiar with how things bond or whatever, you have CH bond, CC, C double bond C, CN, on down the line. You'll need that information and understand that at least to be able to calculate delta H from these bond enthalpies, because you have to identify how many of each type of bond is present in the molecule. So when you do this, you take the sum of the bond enthalpies that are broken, okay, and subtract the bond enthalpies of the bonds that are formed. So which are the bonds that are broken? Is it on the left-hand side or the right-hand side? It's on the left-hand side of the reaction. So on the left-hand side of the reaction, the reactant side, those are the bonds that we're breaking. So what we'll do is we'll calculate out all the energies associated with every bond on that left-hand side. We'll sum all that information up, and that'll be bond enthalpies of bonds broken. And then on the right-hand side, we'll sum up all those energies, and that'll be the bond enthalpies of those formed, and we'll subtract that number from the bonds broken. Here's some energy data on some foods. This is just more for informational. A lot of times, these calorie values that you see on the far right-hand side, those are done through like a bomb calorimetry experiment. That's a common way to do it. And the thing that I always find interesting is fat has by far the biggest energy value, fuel value of proteins, carbohydrates, fats. So that's why it's good to have a certain amount of fat on your body, because it's a good source of fuel. The other one that's kind of interesting is this table of fuel values for fuels. And a couple of things you'll notice. You'll notice hydrogen really has a high fuel value. That's why you see some hydrogen-powered vehicles in that, and people look into that. The other thing you'll see is the petrochemicals are pretty similar. Coal's less, and that's one reason people don't like coal. There's the pollution thing, but then also the energy value is lower. And then the one that's, I think, a bit interesting too is wood. A lot of people burn wood, but you see the energy value, the fuel value is actually pretty low on wood. So let's look at some homework problems though, to get us comfortable with some of these calculations. So the first one is 5.73 that we'll take a look at. So let's see what that one says. So in this one, we're going to use values from Appendix C, where you would look it up, to calculate standard enthalpy change for each of the following reactions. So let's look at this reaction D to see what that is. So the reaction is SiCl4 plus water going to SiO2 plus HCl. Couple things is, the values like the minus 640, the minus 285, minus 910, etc., those would be the values you'd look up in the table. So you have to be given those values, either in a table or someone tells you what they are. So remember, we said, when we go back here, we said for this type of thing, it's, I'm not going to go back all the way, but it's products minus reactants. And so the products are the SiO2, that's the minus 910 value, and then plus HCl, so minus 92.30. We have the 4 in front because that's the coefficient on our balanced chemical equation. So once again, it's important to look at that balanced chemical equation so you know if you need to multiply the delta H value for that molecule or not. Since there's 4 moles of it, we got to multiply it by 4. So there's our products. Then we're going to sum up, we're going to subtract the reactants from it. And so we look at SiCl4, that's the minus 640 value. We have 2 waters, so it's 2 times minus 285.83. And we subtract those numbers from the products, and we get our reaction value of minus 68.3. Okay, let's take a look at this one, 5.83. So with this one, we're going to use bond enthalpies. And once again, we'd look those up in a table or they'd be given to us. And we're going to use the bond enthalpies to estimate delta H. So here's our reaction written out. And it's written out in a way that we can see what the bonds are. And so in this one, remember for the bond energy one, and this is the formula that's a little closer, so I'll go back to that. It's bond enthalpies of broken bonds, of the bonds that are broken, minus the enthalpies of bonds that are formed. And we said that the reactants, that's where we're breaking the bonds. And then on the product side, that's where we're forming. So let's go through the first molecule. So we see that there's 2 moles of that, because there's a coefficient of 2 in front. So it's 2, and let's look at the CH bonds first. How many CH bonds do we have? We have 3. So it's 2 times 3, and then the bond energy for the CH bond is 413. We would have gotten that from the table. What else do we have in that molecule? We also have a CO bond. We have 2 moles of the molecule, so there's our 2. Then we have only one of those bonds, and then it's 358 is the bond energy for CO. So that math covers the CO. The final type of bond we have in this first molecule is an OH bond. Once again, there's only one of those, so we have 2, because there's 2 moles of it, times 1 times 463, which is the bond energy for that molecule, for that bond rather. So we had that molecule done. We had 3 CH bonds, 1 CO bond, 1 OH bond. And then we had 2 of those molecules, so it all got multiplied by 2. The next molecule is O double bonded to O. So we just have one of those, but we have a coefficient of 3 in front. So we have 3 times that bond energy. That takes care of our bond breaking side, right? So if we sum up all of that information, we have our bond breaking information. So then let's go to the forming. So the first molecule, C double bonded to O, there's 2 of those. And so we have 2 moles also. So the coefficient is 2 from the 2 moles. Then we have times 2 because there's 2 of those types of bonds. And then 799 is the bond energy for C double bond O. Then the next molecule, water, H, there's 2 OH bonds there, and there's 4 water molecules, 4 moles of water there. So we have 4 for the coefficient, then 2 for the number of bonds, and then 463 is the OH bond energy. So we would sum up the bond breaking ones, and then subtract from that the sum of the bond forming energies. And then that would give us the minus 1295 kilojoules. So any questions on this problem? Okay. So just to review again, on these types of problems where you're using bond energies to predict what a delta H for a reaction would be, you'd have the bond breaking, which is the reactant side, you're putting energy in to break the bonds, and you'd go through each of the molecules and assess how many bonds are there, what kind of bonds they are, and then how many moles of each of those components is involved. And you use that information to do that calculation. Then you'd subtract the reactant side, which is the bond forming side, and you'd do the same thing. You'd go through, look at the molecules, you'd look at what bonds are being formed, get the bond energy for that, and then multiply it by the number of those bonds and by the number of moles as well. And then you'd sum all that up, and that would get subtracted from the bond breaking side. And that would give you an estimation of your delta H reaction. Okay, that's it for the thermochemistry. If anyone has a question, I'll be glad to answer it. If not, that's it for today. Monday, we will review chapters 3 and 4 in preparation for the exam. And then next Wednesday, we'll have an exam. Okay, thank you.